This is a video to go over lesson 2.3, so the second lesson in chapter 2. Last day we looked at evaluating limits using tables and graphs, and today we're going to be evaluating limits using some what we call limit laws and algebra. Okay, so let's look quickly over these limit laws. I think they'll make more sense when we do actual questions, but they're good to go over. So when you're evaluating limits, if you have two terms that are being added together, you're free to do the limit of both of those terms separately and then add the answers together. Same for subtraction. Same if you have a constant number times a function that you know what the limit is, then you can just multiply that constant times the answer to the limit. And if you're multiplying two terms together, you can do the limit of those separately and multiply the answers, and same for if you're dividing. Okay, you can consider them separately. So those are just basic. We're gonna kind of go over, I think they'll make more sense when we do the examples. The most important limit law, though, is a limit law called the direct substitution property. I'm gonna highlight it. So what that says is if you can evaluate a limit in the x value and it's defined, then you can go ahead and do that, and that's the answer to the limit. So let me show you what I mean by that. So here in this case, we have a polynomial. It's going to be defined everywhere. We're interested in what's the function approaching as x is going towards 5. So if I just try plugging in 5 here, so 5 squared plus 2 times 5 equals 3, or sorry, minus 3. This is 25 plus 10 minus 3. This is 32. And so this is defined. There's no problems doing that. Then 32 is the actual answer. So this is going to happen a lot of times when you're evaluating limits. You don't have to make a big table or anything. There's nothing special happening at x equals 5. There's no hole in the graph or asymptotes or anything like that. So that's what the direct substitution property says. If you can plug in the x value and there's no problems doing that, then you can go ahead and do that. So these next two limits are going to be the same. Here we have a rational function. So we can try plugging in 1. See what happens. So 5 times 1 squared plus 1 all over 1 plus 2. So we get negative 3 over 3. No problems with that. We're not dividing by 0 or anything. Negative 1. Okay. So if that worked out, it's defined, then that's the answer to the limit. Same with this one. Square root of 3 squared plus 3. That would equal square root of 12. Square root of 12 is defined. It's not a negative radicand, so we're good. That's the answer. Okay. So not all limits are this easy, okay? And these are kind of uninteresting. They're just the same values of the value of the function. We're more interested in limits when they can help us understand the graph at points where maybe we can't get x value. So let's look at some examples. We're going to do 4 examples because there's kind of 4 main strategies for solving limits like this. The first strategy we're going to be using is factoring. So I'm going to put the names of the strategies on the left-hand side. Okay, so if we tried to, I'm just going to, for this one, write note. If we try plugging in x equals 4 into here, we have 4 squared minus 16 over 4 minus 4. So that would give you 0 over 0. So we cannot, this is not defined, so we cannot use the direct substitution property right now because it's not defined at x equals 4. So what we have to do is maybe manipulate it algebraically into a form where we can substitute x equals 4. So for this one, we use factoring. So you use factoring when usually in a rational function, maybe there's going to be a canceling that happens. And you can see that the numerator here can be easily factored because it is a difference of squares. So when we write it, you have to be really careful to use your equal signs property. So we haven't evaluated the limit yet, so we need to still write limit as x goes to 4. And all I'm going to do is replace the numerator with its factored form. So it'd be x minus 4 and x plus 4, all over x minus 4. And what we see here is that there's an x minus 4 term on the top and an x minus 4 term on the bottom. And so we get limit as x goes to 4 of x plus 4. Notice I still write limit as x goes to 4 because I haven't evaluated the limit yet. Some students end up dropping that, and then your equal signs aren't being used properly. Okay, now at this point, we can check if we can use the direct substitution property now. If I plug 4 into the x position, yeah, that's going to be defined. So that's when we use the direct substitution property, and we just plug in 4 into that x position, and we get the answer, which is 8. So what this tells us is this function approaches 8 as x approaches 4, even though it's not defined at x equals 4. So probably likely there's a hole in the graph at that point, and it's at y equals 8. Okay. So next one, this time we're having h as our variable. And in this case, the strategy is, so it's kind of already factored in the top. You can actually solve this by a few different strategies, but we're going to do it by expanding. So we're going to expand. So right now we cannot plug in 0 because that would give us a 0 denominator. So we're going to just expand that numerator and see what happens. So when you expand, you have to FOIL. It would be 4 plus 4h plus h squared minus 4 all over h. And now we're going to collect like terms. So notice I have not evaluated the limit yet, so I keep writing limit as h goes to 0. So like terms, these 4's end up canceling out. So that's kind of nice. So I'll have 4h plus h squared all over h. And in a fraction, when every single term has the same, has an h in it, we can cancel it out. So this first term has an h, the second term has an h. You can only do that when every single term has a certain number or a certain divisor. So there's 3 terms in this fraction, and every single one divides by h. So we can cancel an h out of every term. We have not evaluated the limit yet, so I still need to write it. It'll be 4 plus h. And on the bottom, you can write 1 or you can just leave it blank. And now I can plug in h equals 0 because it's going to be defined. So I can use the direct substitution property, and I get 4. Okay, so this function approaches 4 as h approaches 0. So that's the second strategy, which would be expanding. So sometimes if the numerator or denominator is already kind of factored, then you want to expand it and see if that leaves you with something that you can cancel. Okay, next strategy is going to be a little bit different. The strategy you'll use if you see square roots. Okay, so in this case, we cannot plug in x equals 0 because we'll have a 0 denominator. So we have to try something else. I'm going to zoom in a little bit. If you have square roots, you're going to multiply by what's called the conjugate. So I'm going to write the strategy on the side. Multiply by conjugate. And again, you want to use this strategy when you see a square root, typically. So we're going to multiply the top and or the numerator and denominator of this fraction by the same thing. That way we're not changing the actual function because technically you're multiplying by 1 then. And what you want to multiply by is the same square root term, but then the opposite sign of the constant term. So instead of square root of x plus 1 minus 1, we'll do square root of x plus 1 plus 1. And we'll see why we do that in a second. Okay, so the next step, still write the limit. We haven't evaluated yet. We're going to expand the numerator. So we're going to FOIL it out. So in the numerator, we'll have, so when you multiply 2 square roots together, they actually cancel out. So we'll just have x plus 1. That's because the exponents are 1/2, and when you add those together, it equals 1. Okay, and then we'll have plus root x plus 1 from the second two terms, and then we'll have minus root x plus 1, and then we'll have minus 1. On the bottom, do not expand, just leave it as it is. So that's a really important thing. You only want to multiply the conjugate part. You don't want to multiply the other one because this saves you a lot of time and headache. If you do multiply it out, it's kind of just a waste. Okay, so we've got in the numerator, we've got some canceling that can happen. So notice here we have root x plus 1 and negative root x plus 1. So those can cancel out. And also we have x plus 1 and then minus 1. So the 1s actually go away also. So let's see what we've got now when we write it out. So on the top, the only thing left is x. And on the bottom, we have x times root x plus 1 plus 1. So we have one term on the bottom and one term on the top, and they both have an x. So we can cancel those. X goes 0. When you cancel everything on the top, you're just left with 1, so you need to write that 1. And on the bottom, you have root x plus 1 plus 1. Okay, so this looks a little bit simpler. Let's check if we can use the direct substitution property. So if I plug 0 into the denominator, I'm not going to get 0 anymore. So I actually can plug it in. This is when you can drop the limit. Okay, so 0 plus 1 plus 1 would be 1 over root 1 plus 1 would be 1/2. Oops. So this function approaches 1/2 as x approaches 0. Okay, so that's multiplying by the conjugate. So far we've done 3 strategies: factoring, expanding, and multiplying by the conjugate. The last pops up quite a bit also. It is when you have multiple fraction terms. So that is, the strategy is common denominator. So this actually pops up throughout the course, even when we're not doing limits later on. In later chapters, we're going to be using this strategy too to combine fractions together because it just makes things simpler. So when you have more than one fraction term and you can't use the direct substitution property, what you want to try is making a common denominator and putting the two fractions together. So notice the denominators both have an x, but the first one's missing the x minus 2. So we're going to multiply the denominator and the numerator by x minus 2. That's okay because that's like multiplying by 1, so it's not changing the function at all. We haven't evaluated the limit yet, so we still write it. So we get x minus 2 on the top, x minus 2, and then this fraction is x minus 2. Now they have the same denominator, we can add them together. So fractions can be added once their denominators are the same. So x minus 2 plus 2. So you add the denominators, keep the denominator, or add the numerators, keep the denominators the same. Okay, and now we can collect like terms. So negative 2 and 2, they cancel out. Start a new line here. So I just have x left. I have x minus 2 on the bottom. So this fraction has 2 terms, one on the top, one on the bottom, and both the top and the bottom have an x. So those can cancel out. So on the top, when you have nothing left after you've canceled, you just put a 1. And then on the bottom, I've got x minus 2. And now I can use the direct substitution property, because it will be defined as 0. And you get 1 over negative 2 or negative 1/2. Okay, so those are the 4 strategies that you want to use today when you're doing your assignment. If one strategy is particularly hard, you might extra practice like it requires strategy. So again, they were expanding, multiplying by the conjugate, which might be new for some of you, and then finding a common denominator and combining fractions.